So our next speaker is Steve Smith from SepSolve, who will be talking about two-dimensional GC.
Good afternoon all. Firstly, thank you. Some of you may have been expecting Laura McGregor when you turned up for this presentation. She sends her apologies and me in her place as a last-minute replacement, so I hope I can do this justice. So this presentation looks at a project we've been completed recently on volatile profile of oats and the impact of packaging on those volatiles. We've of course used GC TOF for this, and I'll show some new software tools too that help speed up the comparisons. I'm sure many of you here are already familiar with SepSolve, but for those of you who aren't, we are an instrument and solutions provider who are part of the Schaumburg Analytics group alongside Marks International. While Marks are known for their thermal desorption technology and sampling accessories, SepSolve are more focused on the separation, including fast GC and GC, as well as detection with our benchtop 2 time of flight mass spectrometer, and finally with software in the form of data analysis and chemometrics. We work closely with Marks to provide complete solutions. So with the global push to move towards a circular economy, there is obviously an increased focus on reducing waste and reusing more materials. So recently there's been increased use of recycled packaging for food and beverage products, but this obviously brings some challenges because of concerns about chemical interactions between the packaging and the packaged product and how these might affect the product throughout its shelf life. So investigating the migration of the volatiles from food packaging is essential for ensuring safety, quality, sensory integrity of food products. Packaging and labeling materials that include plastics, adhesives and inks can release volatiles that migrate into food. Like you can see in this diagram where we have the packaged oats on the left, the packaging itself and the label, then the external environment. So a number of interactions can occur where volatiles can migrate from the packaging or labeling into the food product, or the flavor volatiles from the food may be absorbed or scalped by the packaging, causing a loss in the quality of the product. And finally, you may even get contamination from the external environment making their way through the packaging into the food product. These can potentially lead to the contamination and alteration of sensory characteristics such as taste and aroma, and understanding these mechanisms is therefore essential to help develop recycled packaging that reduce these interactions and complying with food safety regulations. In this study, we wanted to investigate the impact of packaging and decided to take a closer look at rolled oats. We chose these because they are readily available in a range of different packaging types, and they will readily absorb volatiles that could impact their quality or flavour. In terms of sampling volatiles from food or drinks, the previous approaches have tended to be Headspace or SPME because of their simplicity, ease of automation and low cost, but they come with compromises. With Headspace, there's no pre-concentration and you are generally restricted to smaller volumes, like 1 mil per sample, to prevent peak broadening. So sensitivity is limited, while with SPME, the fibers can be fragile and difficult to use with immersive sampling. And they can get easily contaminated and it reduces their lifetime. And finally, they have a low phase volume of around half a microliter. So again, sensitivity is limited. In this study, we opted instead for a high capacity sorptive extraction, like you can see in the top right of the photo here. These work on the same principle as SPME, but on a much larger scale with around 30 to 65 microliters of sorbent, depending on the phase being used. So this boosts sensitivity. They are more robust and they allow for immersive sampling when needed to. This was automated on the Sentry platform from Marks International, where trap focusing is used to further improve sensitivity, allowing for multiple extractions to be enriched on the trap before it's injected onto the GC, and also allows for water management too. And I wouldn't be doing my job properly if I didn't also mention that with the Sentry platform, the trap focusing actually minimises some of the other drawbacks of headspace and SPME. The focusing of the trap means that higher volumes can be used for the headspace methods while keeping the peaks sharp, and the multi-step enrichment can boost sensitivity for all approaches. So we bought 6 packs of rolled oats from a local supermarket in the UK. These were from 6 different brands labelled A to F and used different types of packaging. There were 2 packaged in cardboard, 1 in paper and 3 in plastic. They were sampled in headspace vials of around 1 gram of each using triple phase high-zorb probes with an incubation temperature of 70 degrees over a 45-minute sampling period. The sampling was automated on the Sentry platform, like I mentioned, and injected onto the GC TOF that you can see here with our Insight flow modulator. Obviously chosen because of the volatiles we were expecting to see in these samples. Each sample was run in triplicate in a randomized order and then processed using tile-based workflows in Crom Compare Plus. So here are the example chromatograms for each brand, and at a glance the profiles for all 6 oats are similar. But we wanted to see if there are any trends that could be linked to the packaging, so that's where the tile-based chemometrics came in. We applied tiles of 12 seconds by 0.75 seconds overlapped at 20% across the chromatograms to give each peak a better chance to be within the center of the tile, and automatically collated the signal for each mass charge in each tile, resulting in over 100,000 unique features. So these features were filtered down to the top 50 that discriminate between the classes for both brand and packaging. To begin with, using PCA, we can see that the triplicate clusters in their individual brands, but there were also trends for packaging type. So the plastic, paper, cardboard packaged oats all seem to separate out along principal component 1, suggesting that the packaging is likely to be influencing the volatile profiles of the oats. The 2 brands of the cardboard packaged oats clustered closely, but the plastic packaged oats had a greater diversity with the brand D separated on principal component 2. And if we look at the load-ins for the principal components, we can see that components like styrene, alpha-methyl styrene and 2-ethylhexanol seem to be responsible for the separation of the cardboard packaged oats A and B in red. And here along PC1, while compounds like beta-myrcene and 2-propanol, 1-ethoxy were elevated in the plastic packaged oats, with brand D having unique differentiators like ethyl cyclohexanone that separate in PC2. So we took a closer look at the differentiators of the 2 key ones found by Crom Compare, which were the 2-ethylhexanol and triacetin. Interestingly, triacetin was only a differentiator of brand D. It wasn't elevated in the other plastic packaged oats, and it is in fact in plasticizers, but it's also an additive in food, so it could be either due to processing for that individual brand of oats or due to the packaging. While 2-ethylhexanol was clearly elevated in both of the cardboard packaged oats, with a small increase in the paper packaged variety too. And this compound can be used in the process to make the plastic coatings that are applied to cardboard that is going to be used for food products. So it does seem like it's a possibility that it originated from the packaging. Out of the top 50 differentiators that were found using feature selection, 33 compounds are identified with some or other feature being duplicates due to adjacent tiles having a hit for the same peak. And you can see them all listed here. Some were brand specific, while a lot seemed to be packaging specific, especially for cardboard and paper. So what we wanted to do next was to see if we could show that these components were also in the respective packaging. So we took half a gram of each packaging and analysed the headspace volatiles in the same way with sorptive extraction. And you can see example chromatograms for each here. But they were again run in triplicate in a randomized order. As you can see in the surface chart stacked at the top, the 2-ethylhexanol was actually the most intense peak in the cardboard packaging. It was about 20% of the total peak area. So it seems likely that this was indeed migrating into the oats A and B and causing it to be seen as a differentiator of their profiles compared to all the other oats. Triacetin, which you saw was elevated in brand D, was indeed the dominant peak in the plastic packaging of brand D again, suggesting it may have migrated. On the other hand, for the paper and other plastic packaging, the dominant peaks were not ones that were seen as differentiators of the oat volatiles. You can just see a close-up view of a few of those across the different brands with ether at the top, found in the plastic packaging for brand E, which was indeed elevated in those oats. Alpha methylstyrene was found in significantly high levels in the cardboard packaging, and again one that was elevated in the oats in cardboard packaging. While there were many compounds that were common across all types of packaging, like the aldehydes such as nonenal, that you can see here in similar levels across all. In fact, 25 of the 33 differentiators of the oats were confirmed at elevated levels in respective packaging. It's therefore likely that the packaging materials were the source of these volatiles, which were subsequently absorbed by the oats packaged within them, while the other differentiators may simply have been due to the growing conditions or processing of the oats, like the drying temperature used, for example. So GC, TOF and the tile workflows have definitely been shown to be useful in mining larger data sets to find trends, but when it comes to identifying problems with packaging and in an industrial setting where this process of running replicates and identifying tiles can be quite time consuming, it just isn't practical. Fast answers are needed to address product complaints or troubleshoot issues, so we wanted to take a look at tools that could tackle that challenge too and make GC more amenable to those industrial applications. So in that situation, wouldn't it be faster to just subtract one chromatogram from the other? Of course, but the issue is that with regular subtraction, the subtracted chromatogram is just as busy as the original. So small differences between the intense peaks dominate the result, like you can see in this example for an essential oil. In fact, this was the same oil, but in one injection, it had been spiked with only one additional compound. So in this scenario, it would take a while to find out what was the truly important peak, especially if you didn't know what you were looking for. And this is where smart subtract comes in. Here we use a probability-based subtraction to suppress the small relative differences in samples, and in this case focus on the key differences, that is the spiking compound, so which here has been isolated effectively with a nice clean background. So let's apply that to the oat samples and take two that were found to be quite similar. So the plastic package brands E and F, which you can see there look remarkably similar. When we apply smart subtract, we can get brand E minus F at the top, where a number of ethers associated with solvents were found. And more worryingly, a chlorinated compound, which are all elevated in brand E. Now, because the subtracted chromatograms retain the spectral information, it's easy to automatically identify the peaks too, and you can see that it was a good match for the chloro compound. Whereas brand F appeared to have higher levels of components that could change the perceived aroma of the oats or cause an odour taint in the case of compounds like pentanol that have a less desirable odour. So as I mentioned, the spectral information is retained, so it makes it much faster to identify all the differences and answer the troubleshooting or complaint issues when they arise with the workflow. It's used when it's used in the industrial setting. You just run the automated peak detection and library searching and get a peak table for all the differences that were seen. So hopefully this study has shown that GC TOF could be an effective tool to help understand the migration of volatile compounds from packaging into food. The level of detail it provides can help develop better sustainable materials and is crucial for ensuring food safety as well as consumer satisfaction. The complexity of the volatile profiles definitely required the enhanced separation of GC for reliable identification of both aroma-related volatiles and packaging contaminants. and automated software aided in identifying key differentiators and trends with the new Smart Subtract tool, also streamlining pairwise comparisons to make the approach more amenable to an industry setting where fast answers are required to address product quality issues or complaints. Finally, I'd like to thank applications chemist James Ogden, who is with us at SepSolve, and Maria Gader, who's here somewhere. So I'd like to thank those. Thank you for listening.